previously, I showed how you can calculate the photon energy presented here using a proportion. And that's the preferred way because it's very simple. But other times you might not be able to avoid sort of going through the sort of full calculations there and getting sort of intermediate values along the way. And so in this video, I'd like to sort of show you how else you can calculate the photon energy, which I think was 1.68. So let's just remind ourselves what we did the sort of simple way here. We said that energy of a photon is inversely proportional to wavelength. And so we can solve this with like a proportion. We'll take the energy we want to know, the energy of this photon with that wavelength, compare it to the energy we do know, 2.96 electron volts for this wavelength. Because it's inversely proportional, this energy corresponds to a wavelength of 420 nanometers. And so they show up on either side of the fraction, right? Like the denominator down here corresponds to like the numerator on the other side. Likewise, the energy that we want to know, the unknown, corresponds to this wavelength here. And once you solve this, you get 1.68. So we sort of know what to expect with a very simple calculation. How else can we get this answer? All right, so we're going to consider this wavelength. All right, C equals lambda times frequency. The speed of light is 3 × 10⁸ meters per second. That equals wavelength times frequency. So if I divide each side by wavelength, okay, then I've solved it for the frequency. The wavelength is given as 740, and the nano is 10⁻⁹ meters. So meters are going to cancel. I'll be in reciprocal seconds of frequency. That's hertz of frequency. 3 × 10⁸ divided by 740 × 10⁻⁹ gives a frequency of 4.054 × 10⁻⁴ hertz, or reciprocal seconds. We can then use the Einstein relation. The energy of a photon is equal to Planck's constant times frequency to calculate the energy, right? Which is kind of what we want, but keep in mind this is going to be in joules of energy. So we'll say the energy equals Planck's constant, 6.626 × 10⁻34. If you're watching this video because you're studying ACE physics, note that the value that they use for this is 6.63. Just like, we know the speed of light a little bit more precisely than this. It's actually 299,792,458. That's close enough to 300 million meters per second. So just kind of round it. The units there are joule seconds, and then multiply it by 4.054 × 10⁻⁴ reciprocal seconds. And so those are per seconds. And so seconds times reciprocal seconds cancels. We multiply those two and we'll just have joules of energy. Keep in mind that we are not in electron volts when we solve this, right? We're in joules. So I have the frequency still in my calculator from this calculation, and I'm going to multiply it now by Planck's constant, 6.626 × 10⁻�34. And I get 2.686 × 10⁻⁹ joules. And then to convert from joules to electron volts, you use 1.6 × 10⁻⁹ joules per electron volt. That's also the value for elementary charge that we discussed previously. So the charge on an electron is called elementary charge, and it is 1.6 × 10⁻⁹ coulombs of charge. Coulomb is the unit of charge in physics. So I have this number in my calculator divided by, remember to use grouping symbols when you divide by something in scientific notation, 1.6 × 10⁻⁹. And I get 1.6788, which indeed, once I round it to the hundredths place, equals with valence. So another way to sort of calculate how many electron volts of energy there are in a photon of a given wavelength, note that nowhere in that calculation did we even need to consider this photon. Right, like this information is extraneous if you know the speed of light and Planck's constant in all the equations. Like we know enough about physics for a single wavelength of light, I can calculate its energy just by using those equations. In order to solve it with a proportion, you have to compare it to something else that's known, right? So like we didn't need any of this 420 nanometer, 2.96 electron volts to calculate the same answer we get if we can compare it. So, if you have something to compare it to in science, that's usually the simpler way. Throughout the history of science, that's what sort of scientists have done. Kepler, compared things to Earth. We still compare things to Earth, right? In astronomy, and say, well, 1 Earth year, Pluto orbits in 250 Earth years, kind of a thing. So that's a mainstay of science, to use proportions to solve things. This has been another worked example with Dr. Schleif, and we'll see.